Hi. For our final FA3 project, the structure we chose was a conical horn antenna, whose main function is to receive and transmit microwave signals. Horn antennas can be identified by the flaring metal horn connected to its narrow waveguide. The horn antenna could be found in several shapes such as a cone, circle, or a rectangle. A waveguide is a structure that guides electromagnetic waves, and in case of a horn antenna, the microwaves. A conical horn antenna is in the shape of a cone with a circular cross-section. They are used with cylindrical waveguides. Horn antennas are popular in the microwave band. Conical horn antennas are renowned for their advantages such as a high gain, which is a high output achieved with a low input. Also, a low VSWR, the ratio of voltage from the maximum node to the minimum node, a relatively wide bandwidth. The antenna can operate on a wide range of frequencies, and it is easy to build because of the simple design and structure. As shown on the diagram right here, this is the aperture, this is the diameter of the waveguide, this is the length of the flare, and this is the opening angle, also known as a throat angle. The length of the flare and the aperture are the two main physical constraints used in the building of a horn antenna. In order to maximize the gain from the conical horn antenna, increasing the aperture is desirable, but the size of the waveguide should be kept as minimal as possible. However, if the waveguide size is slowly expanded into a larger aperture, the more gain is achieved. Therefore, this is achieved as the taper of the horn changes the impedance gradually along the horn's length. This acts like an impedance matching transformer, allowing most of the wave energy to radiate out of the end of the horn into space with minimal reflection, allowing us to acquire a higher gain. Polarization of a horn antenna depend on their shape, and therefore conical horn antennas have circular polarization. Lastly, to achieve the maximum gain for a given aperture, the taper must be long enough so that the phase of a wave is constant across the aperture.
Now we would like to discuss an application of how we can design a conical horn given the frequency and gain requirements. As you can see, we are given a frequency of 8 GHz and a gain of 22 dB. We have an equation of gain which is 20 log pi times the diameter divided by the wavelength minus GF, which GF is basically equal to ATL plus PEL dB, and these ATL and PEL are both the properties of a horn. Moving on with the design problem, we have now a quadratic phase distribution constant S, which is an arbitrary constant, so I just chose a value of 0.8. We need to find the diameter, so rearranging the gain equation gives the following equation for diameter. This is an electromagnetic problem. We have the equation for finding the wavelength, which is V equals to F lambda, where F is the frequency, and we got a wavelength of 3.75 centimeter, and plugging this in the equation of diameter, we get our diameter of 17.45 centimeter. Now our group will like to introduce some methods that are commonly used for the analysis of horn antenna characteristics. These methods are GBMA, which is Gaussian beam mode analysis, then we have mode matching technique, and the third one is finite integration technique. In the video ahead, you will see that we will be discussing about mode matching technique, and then we will show a comparison between mode matching technique and GBMA.
The mode matching technique is used to fetch the description of the internal fields of a horn in terms of the propagation waveguide mode. This technique is used to get the number of steps used and the cutoff frequency of the radiation. In this technique, we replace the actual profile of the horn with uniform waveguide sections, slowly changing in the cross-sectional area for the smooth-walled horns and the corrugated horns. The technique is used to predict the changes in the electrical and magnetic fields within the horn to figure out its transmission and reflection properties. To figure out how many waveguide sections should be used in modal analysis, we use the rule developed by Kuhn and Homack, which states that if the aperture diameter is greater than 1 lambda, then the horn should be divided into 30 sections for every wavelength change in diameter. For example, in our application above, there were approximately 140 sections used to get a significant result. The far field beam pattern results at 100 GHz are shown in the graph. We are using 50 waveguide sections, and it can be clearly noticed that any increase beyond 200 steps produces minimal changes to the result, describing that the horn produces poor results when it's divided into more than 200 steps. The same technique is used to figure out the cutoff frequency. Once a suitable frequency is obtained for a horn operating at 100 GHz, models of higher frequencies were produced to investigate the effects of the cutoff frequency within microwave wizards at higher frequencies. For example, a horn operating at 300 GHz has length and aperture dimensions of the original horn divided by 3. This concludes that as the operating frequency increases, the compilation cutoff frequency can be lowered below the recommended 10 times of the operating frequency. The two analysis techniques, GBMA and MMT, used for smooth-walled conical horns, produced results which were in agreement with each other. The GBM technique can be used to accurately reproduce the radiation pattern of a conical horn antenna faster than any other technique, while still producing accurate results.
When talking about open EMS implementation of conical horn antenna, we begin by declaring physical constraints of the horn. You can refer to figure 1.0, where it shows that the aperture's diameter is 40 mm, and so the radius of the aperture becomes 20 mm. The horn length is said to be 50 mm, and the horn feet length is also said to be 50 mm, whereas the thickness of the horn is said to be 2 mm. Also, the horn length is set at the direction of the z-axis. When talking about the horn's opening angle, it would be 2 times alpha, which equals to the value of 20 divided by 180 times pi radians. Lastly, the frequency range of interest starts from 10 GHz and stops at 20 GHz, where the behavior of the antenna will be tested. And the specific frequency of interest is defined as 15 GHz.
We define simulation parameters in 2 objects. All parameters that define the type of simulation, boundary conditions, number of simulated time steps, etc. are saved in the FDTD object. In our specific case, we pass the NRTS, which stands for max number of time steps, 30,000 to define the max number of time steps, and criteria, which basically tells the simulation to stop if the energy has decayed by this value, and 10 to the power of -4 to define end criteria. The boundary conditions are PML_8. PML stands for perfectly matched layer observing boundary condition, and it uses X number of cells, and in our case it uses 8. Finally, the FDTD object is fed into the previously created object, and the boundary conditions are passed. Now both of these are set as the boundary conditions. The second object we define simulation parameters in is a CSX. The information about the scattering structure and the shape of the surface is stored in the CSX cat object. The simulated structure can be constructed from a variety of predefined shapes, such as spheres, cubes, cylinders, wires, etc. The structure to simulate is saved in the same structure as the simulation mesh, light sources, and field dumps. For our specific antenna, we created a mesh of the cell size of lambda divided by 20. The mesh in the x direction was created in correspondence to the horn's radius and was also duplicated in the y direction, whereas the mesh in the z direction was created in correspondence to the horn's feet, also known as the waveguide length, and so both of these were passed on into the defined rectangular grid function, which creates a mesh around the antenna which takes the form of a rectangular grid. The material property of the antenna is metal. Metal is a good choice for the material of the antenna since it's a perfect electric conductor. Conical horn here, defined, is the name of the assigned property, while CSX is the original structure. The x, y, and z coordinates of the horn are declared with respect to its geometry. Finally, the conical horn is set up using the rotated polygon function, and its aperture is defined using trigonometry. To apply the excitation, we first need to define the start and the stop points. Start and the stop are the respective coordinates of the waveguide of the port box. We also feed the horn radius. We feed in the mode, which is TE11, and the polarization and the excitation amplitude. The polarization angle over here is defined to be 0, whereas the excitation amplitude is 1. We feed these parameters in the add circular waveguide port function, which creates a circular waveguide port. We now add a dump box. Adding a field dump in OpenEMS is a two-stage process. Firstly, a dump box property is added to the CSX structure with the given name and properties. Which fields will be saved and other options such as the file type, interpolation mode, etc. are defined. In the second step, the geometry of the field dump is defined by adding a primitive to the field dump. Our specific dump box saves the electric field step for each type step in the box. Using the function create n2ff box, we create surface dump boxes surrounding the structure. CSX is the data structure to be manipulated. N2ff is the name of the N2ff calculation. Start and stop are the start and stop coordinates for the N2ff box and contains all the structures. Directions here is a 6x1 array which shows the directions which are enabled or disabled for the N2ff calculations. The number of the arrays represent basically x minus direction, x plus, y minus, y plus, z minus, and z plus. Ones and zeros stand for which direction is enabled and disabled. So for our specific one, the x minus is enabled, x plus is enabled, y minus is enabled, y plus is enabled, our z minus is not enabled, and our z plus is enabled. Then we create a temporary file path as well as a temporary file. Our temporary file is called horn_ant.xml, which is the format of the file. Then we write this file using write OpenEMS function, and we feed in the simulation path, the CAD, FDTT, and the CSX. We then show the structure, the CAD model for the structure using the CSX geom plot model, and we tell OpenEMS to run using the run OpenEMS function.
For the following MATLAB code, we are plotting the S11, which is the reflection coefficient of the horn antenna against the frequency range we defined in the beginning of the code. The scale of S11 is 20 log 10, and we are taking the absolute value of S11. For this part of the code, we are plotting the far field contours on H and E plane, both on the same graph. The theta ranges are converted to radians from degrees, and the scale to 10 log 10 for directivity. Nextly, we are plotting the electric far field of the conical horn antenna as seen from the x-axis using the polar ff function. At the end of the MATLAB code, we use the plot ff 3D function to plot the 3D model of electric far field for the conical horn antenna over theta and phi range. We then normalize the electric far field and simulate it.
Now we are going to discuss the OpenEMS results. As we can see, this first graph right here is to compare the reflection coefficient's magnitude with the frequency applied. So we have frequency on the x-axis and the reflection coefficient on the y-axis. Our frequency of interest is 15 gigahertz, and as we can see, the maximum value of the magnitude peaks right around 15.3 gigahertz. Therefore, the simulation results make good agreement with the expected results, and that is exactly what we wanted. Moving on, the second graph we are going to discuss is the electric far field pattern at 15.0 gigahertz. Again right here. So we have theta on the x-axis and the dielectricity on the y-axis. And exactly as we have in the description below, the phi angle is 0 degrees for the H-plane sectorial horn, and phi is 90 degrees for the E-plane sectorial horn. So the above graph, this graph right here, basically compares the far field pattern for these planes, and the directivity is maximum for both of these planes, which is correct as the gain has to be largest at theta equals 0. So in this graph right here, we can see that the gain is largest at theta equals 0. Now we're going to discuss figure 3 and figure 4 results. This is the electric far field of the conical horn antenna as seen from the x-axis, or being measured with respect to the phi angle, as you can also say. And finally, for figure 4, we're simply looking at the 3D patterns of the electric far field, and the reddish part right here, which is the top section of the radiation on the schematic shown, is the largest value of the field. And this summarizes our EMS results.
That is the end of our presentation. I hope you guys enjoyed it. Following are the references for our project. And there we have a client request. Dr. Bakr, please mark our exams leniently. Thank you very much.